Hi, we are from Group 16 and we're going to explain on the applications of using MATLAB.
Hi guys, I'm going to be talking about the Simulink algorithm creating for robots. Now, there are a few steps to this process. Let's start with the first one, where we have to connect to and control our robot with the algorithms that we have to develop. Now, these hardware agnostic algorithms, we have to connect them to the robot operating system, which we have two systems, ROS and ROS2. Then the third step is to connect to a range of sensors and actuators. We do this so that we can control signals or analyze many types of data. And then we eliminate all the hand coding automatically by generating a code for embedded targets like microcontrollers, FPGAs, GPUs, and we can do this in many languages like C, C++, VHDL, Verilog, structured text, and etc. Then we have to connect to a low-cost hardware such as Arduino or Raspberry Pi using pre-built hardware support packages. And then we simplify the design reviews by creating shareable code and applications. And lastly, we are then able to work with legacy code and integrate with existing robotic systems. There you have it, a complex robotic systems that is made using MATLAB and Simulink application. Thank you. Let's move on to the next slide now. In this part of the slide, we are talking about path planning and navigation for autonomous robots. Now, if you see the link below, it's actually a demonstration of how to simulate a self-parking car with just three components. The first one, a path, second, a vehicle model, and a path following an algorithm. These three lessons can be applied to all autonomous robots, not just self-driving cars. But how do we do it? So let's see. We start in MATLAB, where we can create a map of the environment. Next, we generate a path for the robot to follow using built-in path planners. And then we use Simulink to create the vehicle model and customize it to be as complex as we need. And lastly, this is where we built in algorithms like I talked about in the first slide, and blocks in MATLAB and Simulink to create the path following algorithm. And there you have it. This is how it works.
Hi, my name is Muna Yilate. I'll be talking about MATLAB uses. First of all, collecting sensor data. Sensors such as camera. Sensors can be connected via robot operating system and send messages. The messages can be converted into MATLAB data that is ready for analysis and visualization. The large data sets of batch processing, sensors calibration, or transformation can be automated common sensor processing of workflows. Next, perceiving the environment, in which can detect the object tracking, motion estimation, 3D point cloud processing, and sensor fusion. Also allow to learn deeply about the image classification regression in future with convolutional neural network. In short name is CNNS. Lastly, can convert the algorithm into C or C++, fixed point, HDL, or CUDA code automatically. That's all from me. Thank you.
As referred from Mihir Akarya, if you want to autonomously navigate a robot or to park a self-driving car in an unknown environment, you need to first acquire the map of the environment and keep in track of the robot's location. Simultaneously, localization and mapping, also known as LAM, helps you to generate the map while simultaneously localizing both of the robot related to this map without the need of GPS. Algorithms for robot manipulators can be designed, simulated, and implemented with model-based design using Simulink blocks in Robotic System Toolbox. You can easily implement algorithms like computed torque control, which can further be used to perform safe trajectory tracking control for human-robot collaboration. This is one example for mapping and also navigation. This example shows how to use rapidly exploring random tree (RRT) algorithm to plan a path for a vehicle through a known map. Special vehicle constraints are also applied with the custom state space. You can tune your own planner with custom state lists and patch validation objects for any navigation application. These two visuals are part of the steps. These are the steps for the rapidly exploring random tree RRT algorithm. The first one is to load occupancy map. Load an existing occupancy map of a small office space. Plot the start and goal poses of the vehicle on top of the map. This is like what I have shown in the previous slide. And then the steps are followed by define state space, plan the path, plot the path, and customize Tubin's vehicle constraints. Due to the time constraint, I will end my presentation here and pass to Wafi to explain on the designing hardware platform.
Hello, allow me to introduce myself first. My name is Wafi, and I would like to explain about the next part, which is designing the hardware platform. In this part, we have to design and analyze 3D rigid body mechanics, such as vehicle platforms and manipulator arms, and actuator dynamics, such as mechatronic or fluid systems. After that, we have to apply in Simulink. In this part, we can work directly with existing CAD files by importing the URBF files or Unified Robotic Description Format directly into Simulink or from CAD software like SolidWorks and Onshape. And then we can add constraints such as friction and model multi-domain systems with electrical, hydraulic, or pneumatic and other components. Once it is in operation, we have to reuse design models as digital twins. The next part is we have to communicate with embedded targets using several protocols, including CAN, EtherCAT, and 802.11. In communicating with other platforms and targets, we have to use digital, RF, and other wireless technologies to connect to hardware. But remember, this hardware must be supported by TCP, UDP, I2C, SPI, Modbus, and Bluetooth serial protocols.